Hello everyone, I will present you our paper titled Seeding Active Learning for 3D Semantic Segmentation. This paper is a collaboration between École de Bonn and Valeo AI teams. Our work focuses on the initial set selection for active learning in the context of 3D semantic segmentation, which remains unexplored so far. Here you could see the active learning cycle. In each cycle, we select data from unlabeled pool based on our budget using an acquisition function. We annotate it and add to our labeled pool. Then we train a model using all the annotated data pool and go back to first step to select next portion from unlabeled data pool. But how do we select the data to label at the very first step? So far the approach for this selection is random selection. However, random selection is not optimal. In this class, we present 4 active learning methods trained using different initial sets or seeds. Each dashed line is a training with a randomly selected seed, and the solid blue lines correspond to the average of all trainings. From these results, we could infer the following. First, there is a high variability between different random draws. Second, we see that the variability is even larger at first active learning cycles. Third, if we are unlucky and draw a bad seed, we could achieve really bad performance. Even if we are not that unlucky, then most of the time we will get the average, and we see that average is suboptimal. We could do better. And finally, we see that the performance ranking of active learning methods changes depending on the seed. In order to overcome these problems, we propose a method to select the lucky seed for 3D point cloud data. While selecting the data, our method aims to maximize the intra and interscene diversities. Interscene diversity helps to select the data which contains high variety of information such as objects. On the other hand, interscene diversity enables to select different types of scenes. Every point cloud dataset contains 2D images which are aligned with 3D data. In order to model each scene, we use self-supervised 2D features which contain following advantages compared to 3D counterparts. First, 2D self-supervised methods are trained on larger datasets so that they can generalize better. Second, they are less sensitive to data, and also they have good discriminability properties. Here we show interesting diversity calculation on 2 example point cloud scenes I and J. We utilize all 2D images for each scene to extract self-supervised features. Then we calculate the average pairwise feature dissimilarities for each scene. If a point cloud scene contains variety of objects, we expect it to have a high intrascene diversity. Next, using the same image features, we calculate the interscene diversity score between all scene pairs. Here, our goal is to select scenes which are different from each other. And final diversity score between 2 point cloud scenes is obtained by multiplying intrascene diversities of each scene and their pairwise interscene diversity. We denote this final diversity score as EIJ. After calculating final pairwise diversity metric between all scenes, we create a fully connected graph. In this graph, the vertices are the scenes and the edge weights are the pairwise diversity metrics between the scenes. Next, we solve the optimization problem to select the scenes which have the highest pairwise diversity values within the given budget. When seeds are selected by our method, SEEDAL, active learning methods perform better or comparable to the luckiest random seed performance. In this class, we present our method's performance on an indoor dataset S3DIS and also an outdoor dataset Semantic Kitty. Our method achieves better performance compared to strong k-means based baselines and random seeds. For more experimental results and details on our baselines, please refer to the paper. Finally, we experimented with various 2D and 3D self-supervised features. All of these features perform better than random selection, and 2D features consistently outperforms 3D features. Our code is publicly available. Thank you for your attention.